Now the question we ask is, does existence of all directional derivatives imply continuity of the function? So this is the question. Does existence of all directional derivatives imply continuity of the function? Well, the answer to this question is no. That can be shown by the following example. Let us look at this function. F of xy equals to xy square divided by x square plus y to the power 4. If xy is not the origin, it is 0 if xy is equal to 0, 0. Now I am going to check that f is not continuous at the origin. So what I do is I approach 0, 0 through the path x equal to my square. If I do that, then f of my square y, that turns out to be my square times y square, that is m y to the power 4 divided by x square now means m square y to the power 4 plus y to the power 4, which is m by 1 plus m square. So if I take limit y going to 0, it is anyway m by 1 plus y square. It does not depend on y, and the limit depends on m. So if I go through different paths, I get different limits. So this implies f is not continuous at 0, 0. But then what about the directional derivatives? First note that the usual partial derivatives exist, because limit h going to 0, f of h0 minus f of 0, 0 divided by h turns out to be equal to 0, because f of h0 is anyway 0, follows from the definition of the function. So is f of 0, 0. So this quotient is always 0. Hence the limit is also 0. Similarly, limit h going to 0, f of 0h minus f of 0, 0 divided by h, that is also 0, because f of 0h is 0, and so is f of 0, 0. Now the question is about other directional derivatives. So let me choose a vector u1, u2 such that u1 not equal to 0 and u2 not equal to 0. Because if one of them is 0, that case I have already taken care of in the usual partial derivatives. Now we look at the limit h going to 0, f of t u1 u2 minus f of 0, 0 divided by h. This is same as limit h going to 0, f of t u1 t u2 minus f of 0, 0, which I know is 0. Sorry, this is, instead of t, it should be h. Instead of t here, I have h, because the increment is given in terms of h, divided by h. Now I just write down the definition of the function. This is limit h going to 0. Now x y square, that means h u1 into h square u2 square divided by x square, that means h square u1 square plus y to the power 4, that means h to the power 4 u2 to the power 4, but then there is an 1 by h, so that sits here. If I calculate, what I get is limit h going to 0, u1 u2 square, because in the numerator I have an h cube which cancels with the denominator. I get u1 square plus h u2 to the power 4. That limit certainly is u1 u2 square divided by u1 square, that is u2 square by u1. So the limit exists, and it certainly makes sense as I have chosen my u1 u2 both to be not equal to 0. So you see that directional derivatives exist in the direction of any vector, but at the same time we have proved that the function is not continuous. So existence of all directional derivatives can never be a replacement of existence of derivatives. So in the next lecture we are going to see how to define derivative of a function of two variables. Now we come to the question of differentiation of functions. So for the sake of simplicity, we will assume that the functions we are going to look at, they are functions from R2 to R. And the theory we are going to develop, it essentially works similarly if you go to R3, R4 or Rn. The most fundamental case is to understand the case of R2 first. So question again is how to define derivative of a function. So for that, let us again look back first at the definition of derivative of a function at a point x0 if the function is from R to R. So let us look at a function f from R to R. Then derivative of f at x0. How do we define this? Well, it says that limit h going to 0 f of x0 plus h minus fx0 divided by h. If this limit exists, then we say that the function is differentiable at x0, and that we call f prime x0. So the derivative of a function at a point x0 is just a number. So an analogous way of expressing this is that limit h going to h0, h going to 0, f of x0 plus h minus f of x0 minus f prime at x0 times h divided by h equal to 0. So we say that a one variable function f from R to R is differentiable at x0 if there exists a number called f prime x0 such that f of x0 plus h minus f x0 minus f prime x0 times h divided by h is equal to 0. Okay? An equivalent expression again is limit x going to x0 fx minus fx0 plus f prime x0 into x minus x0, this whole thing divided by x minus x0 is equal to 0. This is another way of saying the fact that f is differentiable at x0. Now we are going to generalize using this viewpoint on R2. So what does this say? This implies that the function x going to fx0 plus f prime x0 into x minus x0 is an approximation of the function f at x naught, and also the graph. So this is one. Second one is the graph of the function x going to fx naught plus f prime x naught into x minus x naught yields the tangent line to the graph of f at x naught fx naught. Okay, so mere existence of derivatives gives you the best linear approximation of f at x naught, and that line which you get is essentially the tangent line. Now this is the viewpoint we are going to take when we go to functions of several variables. So what is the definition now? So we come to the definition of derivative. Suppose f is a function from R2 to R. Then f is called differentiable at a point x naught y naught if there exists a vector alpha 1 alpha 2 in R2 such that limit hk going to 0 0 f of x naught plus h y naught plus k minus f of x naught y naught minus the dot product of the vectors alpha 1 alpha 2, by this dot I mean the dot product hk divided by the norm of hk. This is equal to 0, and in this case, that is if the limit exists, the vector alpha 1 alpha 2 is called the derivative of f at the point x naught y naught. Okay. Now the question is, there are so many questions to answer now, that given the function f, how do I calculate alpha 1 and alpha 2? That is the most fundamental question. Second one is this definition of derivative all right? In the sense, does this imply that the function f is continuous? So we'll go to answer those questions. First, let me tackle the question that if I already know that the function f is differentiable, how to calculate these vectors alpha 1 and alpha 2, which is going to be the derivative of f. So let us go to this theorem now. So suppose f is differentiable at x naught y naught, then as in the previous definition, we know there exist vectors alpha 1 and alpha 2 such that this limit is 0. I say then alpha 1 is fx at x naught y naught, and alpha 2 is fy at x naught y naught. That is, if the function is differentiable, then the derivative is given by being a vector. Now it should be a tuple of numbers, two numbers. Then the first number is the partial derivative of f with respect to x at the point x naught y naught, and the partial derivative of f with respect to y at the point x naught y naught. So let us come to the proof of this. Let us say I define epsilon of h, which is epsilon hk. So h always stands for the vector hk. Then what is this epsilon? This is f of x naught y naught plus hk minus f of x naught y naught minus alpha 1 alpha 2 dot hk divided by norm hk. So it is essentially the difference quotient, which I am giving a name. I call it epsilon h. Then I know f differentiable at x naught y naught with derivative alpha 1 alpha 2 implies that limit hk going to 0, epsilon hk equal to 0. This is the definition of derivative. Okay. Now I am going to have a particular choice. So let, instead of hk, I take my h to be equal to t0. So I am making k to be equal to 0 and h is equals to t. Then what is epsilon t0? I just write down the quantity. It turns out to be f of x naught plus t y naught minus f of x naught y naught minus now alpha 1 alpha 2 dot t0. Okay, but since alpha 2 times 0 is 0, what I get is alpha 1 t. Now I have to look at norm of t0. Now norm of h in this case is just mod t. So I get mod t here. Okay. This then implies that limit t going to 0, f of x naught plus t y naught minus f of x naught y naught divided by t equals to alpha 1. This precisely implies by my definition that alpha 1 is equal to del f del x at x naught y naught, or fx at x naught y naught. The exactly similar kind of argument by choosing h equal to 0t implies that alpha 2 is fy at x naught y naught. This implies finally that the vector alpha 1 alpha 2 is actually given by fx at x naught y naught comma fy at x naught y naught. So if I know that a function is differentiable, then calculating its derivative is not very non-trivial. All I have to do is I have to calculate two partial derivatives of f with respect to x and y and evaluate them at the point x naught y naught. That gives me a tuple of numbers. That is the derivative of the function at x naught y naught. But some care has to be taken here, because if you follow the proof, then you must have noticed by now that it is very important to use the fact that f is differentiable. If I assume f is differentiable, then the derivative of the function is given by the partial derivatives. It is no way true that if the partial derivatives just exist at a point, then the function is differentiable there. We will come to that. Just at this point, I will note that if I assume that f is differentiable, then the derivative is given by the partial derivatives. Now let us go to another important question, that also I will put as a theorem. If f is differentiable at x naught y naught, then f is continuous at x naught y naught. Now the proof of that is not very difficult. So we come to the proof. Now f is differentiable at x naught y naught implies there exists a vector alpha 1 and alpha 2 such that modulus of f of x naught y naught plus hk minus f of x naught y naught minus alpha 1 h1 plus, well, alpha naught h plus alpha 2 k, this modulus is equal to norm of hk times epsilon hk, where epsilon hk goes to 0 as hk goes to 0, 0. This is just the definition of derivative of a function. Now I just look at f of x naught plus h, y naught plus k minus f of x naught y naught. I just write this now as, I can say that this is less or equals to, this is less or equal to f of x naught plus h, y naught plus k minus f of x naught y naught minus, well, I will have minus here also, minus alpha 1h minus alpha 2k plus alpha 1h plus alpha 2k. Okay. Now this then is equal to norm hk times epsilon hk, and now let me just write down this extra portion as, I will say, less or equal to alpha 1 norm hk plus alpha 2 norm hk. I am just using the fact that mod h is less or equal to square root of h square plus k square. Okay. So I finally get that this is equal to epsilon hk times norm hk plus norm hk times a constant which is mod alpha 1 plus mod alpha 2. Now as hk goes to 0, this implies then that epsilon hk anyway goes to 0, norm hk goes to 0, the rest is a constant. So this implies that f of x naught plus h, y naught plus k goes to f of x naught y naught. So the argument is this right hand side goes to 0 as hk goes to 0 0, because epsilon hk goes to 0 and norm hk also goes to 0. That means the left hand side by sandwich theorem also goes to 0. That means f of x naught plus h, y naught plus k goes to f of x naught y naught. But that is precisely continuity of f at x naught y naught. So this implies that the function f is continuous. So then this definition of derivative looks like will be a truthful generalization of the one variable case of differentiability of a function, because it is giving me continuity. The geometric interpretation of it will come to later. We will now try to inquire about the connection of differentiability with partial derivative. Now let us come to a sufficient criteria for existence of derivatives. So I will prove it as a theorem. It is about that how to connect differentiability of a function through the partial derivatives of the function. So suppose f is a function from R2 to R. If the partial derivatives fx and fy are continuous in a neighborhood, which I will write in short as NBD, in a neighborhood of x naught y naught, then the function is differentiable at x naught y naught. Notice that as I said that the partial derivatives fx and fy are continuous in a neighborhood of x naught y naught, that simply means, that certainly means that the partial derivatives exist, otherwise there is no meaning of saying that they are continuous. But the point to note is that just the mere existence of partial derivatives does not tell me that the function is differentiable at x naught y naught. I am imposing an extra condition of continuity on the partial derivatives that gives me differentiability of the function. Now we will prove this result, and after that we come to the question that is it true that if just the partial derivatives exist, then the function is continuous. Well, that can be answered very simply. We will come to that. First, let us try to prove this result. So how do we proceed? Let us say capital X naught stands for x naught y naught, and capital H stands for hk. Okay. In that light, let us look at limit capital H going to 0, f of x naught plus h minus f of x naught minus fx at x naught times if I want to show that the function f is differentiable, I should check somehow that this limit is 0. Okay, now let me write down all these quantities. F of x naught plus h, y naught plus k, minus fx at x naught times h minus fy at x naught times k divided by norm h. Now this quantity I write as limit h going to 0 f of x naught plus h, y naught plus k minus f of x naught, y naught plus k, these are the terms I am introducing, plus so these two terms was not there earlier, I have introduced them, minus f of x naught y naught, then the rest of the terms as usual, fx at x naught now look at this first term. If I fix y naught plus k, then it becomes a function of one variable. If I fix the second coordinate, then I get a function of one variable, and there I can apply the mean value theorem. Similarly, I am going to look at this and this. Here what I do is I fix the first coordinate, then in the second variable I can apply the one variable mean value theorem. So what do I get if I do that? I get limit capital H going to 0. Let me write it in this form. I get fx at some point c1 times h plus fy at some point c2 h k. I will explain what are these c1 c2s, minus fx x naught h minus fy x naught k divided by norm h, where c1 it is a point of the form x naught plus alpha h y naught plus k, and c2 is a point of the form x naught y naught plus beta k, where alpha less 1 beta less 1. This is by the standard one variable mean value theorem. Now the point to note is that I can write that this is less than or equal to limit h going to 0 modulus of fx c1 minus fx at x naught plus modulus of fy c2 minus fy x naught. This simply follows by the fact that modulus of h by norm h is strictly less than 1 and modulus of k by norm h is less than or equals to 1. Okay. If I use this, then I come to this step, and now I am going to use the fact that the partial derivatives fx and fy are continuous. Notice that if hk goes to 0, 0, if little h and little k, if they go to 0, then the points C1 and C2, they go to x0, y0. That is very simple from their expressions. So once again, if little h comma little k goes to 0, 0, that implies the points C1, C2s, they converge to x0, y0. But since fx and fy are continuous functions, then this goes to 0. So in the last step, I am actually using the fact that partial derivative of f at x in the x direction and in the y direction are actually continuous functions. So finally, this limit goes to 0, and hence the difference quotient which I have started with, that is this difference quotient now goes to 0. This implies that f is differentiable at x0, y0. Of course, then it has to follow that the derivative of f is given by the partial derivatives. That is why in the first place I have chosen my alpha 1, alpha 2, the vectors, to be fx and fy, and started calculating the difference quotient. So we are sure now that if the partial derivatives are continuous in a neighborhood of a point, see, the neighborhood is important because C1 and C2 lie in the neighborhood of x0, y0. They are not really equal to x0, y0. So if those points converge to x0, y0, then the partial derivatives should also converge to the partial derivatives at x0, y0. That is the continuity which we are going to use. So the continuity of the partial derivatives in a neighborhood of a point x0, y0 implies that the function is differentiable, and then the derivatives are given by partial derivatives. So now the question remains that if it is just the mere existence of partial derivatives, does that imply f is continuous? Well, we have already seen some such example. I will again repeat that example here. I look at the function f of xy is equal to xy square divided by x square plus y to the power 4, where xy is not equal to 0, 0, and it is 0 if xy is equal to 0, 0. For this function, we have seen that the function is not continuous at 0, 0, but all the directional derivatives exist. So in particular, the partial derivatives exist, that is in the direction of x and y. But then the function cannot be differentiable simply because the function is not continuous. If f is differentiable, f had to be continuous. But this function is not differentiable because it is not continuous at 0, 0. But see, all the directional derivatives exist. That means in particular partial derivatives also exist. That means just existence of mere partial derivatives can never give you differentiability, simply because mere existence of partial derivatives will never give you continuity of the function. And if the function f has to be differentiable, it has to be continuous. So you need continuity of the partial derivatives. That continuity cannot be resolved, cannot be dropped. So if the partial derivatives are continuous, then the function is certainly differentiable, and the derivative is given by partial derivatives. On the other hand, if I already know that the function is differentiable, then I know that its derivatives are given by partial derivatives. So that is all I wanted to say about the connection with partial derivatives. Now let's proceed with the lecture. Our next topic is a bit technical in nature. It's called the increment theorem. I'm going to prove it because I'm going to use it very soon. So let's start with the statement of increment theorem. So what does it say? So suppose if from R to R, so the function is from R2 to R, is differentiable at x0, y0, then we can write that f of x naught plus h, y naught plus k minus f of x naught y naught is equal to fx at x naught y naught times h plus fy at x naught y naught times k, nothing new so far, but now plus epsilon 1 hk, so it's a epsilon 1 depends on hk, that is what I mean here, times h plus epsilon 2 hk, that means epsilon 2 also depends on hk, times k, where epsilon 1 hk goes to 0 as hk goes to 0 0. Similarly, epsilon 2 hk also goes to 0 as hk goes to 0 0. So the only difference here with the definition of derivative is, there I just had epsilon hk, here I am breaking it into two parts, epsilon 1 hk plus epsilon 2 hk. This form is going to be handy to prove certain results, that's why I am going to prove it. The proof is not very difficult, so we start with the proof the following way. So as f is differentiable, I know that f of x naught plus h, y naught plus k minus f of x naught y naught minus fx at x naught y naught times h minus fy at x naught y naught times k, that is equal to some epsilon hk times norm hk, where epsilon hk goes to 0 as hk goes to 0 0. By differentiability of f, of f at x naught y naught. Now I am going to play around with this epsilon hk times norm hk. What I do is, I write this as epsilon hk divided by norm hk times h square plus k square. That I can do because the expression of norm hk is square root of h square plus h square. So what I am doing is, I am multiplying the numerator and the denominator by square root of h square plus k square. So this now I write as epsilon hk times h by norm hk times h plus epsilon hk times k by norm hk times k. So now I define epsilon 1 hk to be equal to epsilon hk times h by norm hk. Similarly, epsilon 2 hk means epsilon hk times k by norm hk. Okay, then I got the required form. Only thing now I have to prove that as hk goes to 0 0, epsilon 1 hk and epsilon 2 hk, they go to 0. Now you just simply notice that modulus of h by norm hk is lesser or equal to 1. Similarly, modulus of k by norm hk, that is also lesser or equal to 1. That means this is a bounded quantity, so is this, and as hk goes to 0, 0, I know that epsilon hk goes to 0. So anything bounded times a quantity which goes to 0, then the product also goes to 0. So this implies that epsilon 1 hk goes to 0, 0, goes to 0 as hk goes to 0, 0. Similarly, epsilon 2 hk also goes to 0 as hk goes to 0, 0. So that proves the increment theorem, which now I am going to use in something called chain rule. So what is a chain rule? So suppose I have a function f from R to R, and g is another function from R to R. Assume that f, g are differentiable. Then I can look at the function f compose g. At x, it is f of gx. Now I want to know what is f compose g prime, the derivative at x naught. This we know by the one variable chain rule is f prime at gx naught times g prime at x naught. This is quite frequently used. Now I want a several variable analog of this, that is in 2 dimension. So here the setup is exactly like this, that I have a function f from R2 to R, and I have two functions, one is x from R to R, other is y from R to R. Assume that f, x, y are all differentiable functions. Once I know this, I can create another function. So I define w of t equal to f of xt comma yt, and I want to know about the differentiability of w at a point t naught. This is precisely the chain rule which we are going to prove. So the theorem I am going to prove is that w prime at a point t naught is del f del x at x t naught y t naught times x prime t naught plus del f del y at x t naught y t naught, let me put brackets here, times y prime t naught. A standard way of expressing is that this is fx times x prime t naught plus fy times y prime t naught. So this fx fy's here stand for that the partial derivatives at x t naught y t naught. Okay. So this is what we are going to prove now. Fine. So how do we start here? First, I define certain things. I define h1 to be equal to x of t naught plus h minus x t naught divided by h, and h2 that is equal to y of t naught plus h minus y of t naught divided by h. Notice here little x and little y stands for functions, in fact differentiable functions. Now using this, let me start with limit h going to 0 w of t naught plus h minus w t naught divided by h, because w is a function from R to R, so I use the standard definition of differentiation. This now is same as just by writing down the definition of w, that is f of x t naught plus h y t naught plus h minus f x t naught y t naught divided by h. So this then is same as limit h going to 0 f of I look at now my definition of h1, that is x t naught plus h minus x t naught by h, okay, and h2 equals to y t naught plus h. I define h1 equal to x t naught plus h minus x t naught, and I define h2 equal to y t naught plus h minus y t naught. Now I start with the usual definition of one variable derivative, that is limit h going to 0 w t naught plus h minus w t naught divided by h, that is limit h going to 0 by writing down the definition of the function w, it is f of x t naught plus h y t naught plus h minus f x t naught y t naught divided by h. Now I am going to use the increment theorem. By increment theorem, this is same as limit h going to 0 fx at x t naught y t naught times h1 plus fy at x t naught y t naught times h2 plus epsilon 1 h1 plus epsilon 2 h2 divided by h, where I know that epsilon 1 epsilon 2 they both go to 0 as h1 h2 go to 0. This is from the increment theorem. Now I write it in a different form, that this is same as limit h going to 0 fx at x t naught y t naught times the definition of h1, that gives me x t naught plus h minus x t naught divided by h plus fy at x t naught y t naught times y t naught plus h divided by h. This is by using the definition of h1 and h2, then plus the extra terms plus epsilon 1 h1 by h plus epsilon 2 h1 by h. Now let us look at the limits of each terms. The first term, this certainly goes to fx at the point times x prime at t naught. The second term goes to fy at the point x t naught y t naught times y prime at t naught. Here also I have at t naught, x prime at t naught. So now I am bothered about the last terms. All I know is as h1 h2 goes to 0 0, epsilon 1 and epsilon 2 goes to 0. Now as h goes to 0, then what is h1? That is x t naught plus h minus x t naught. Since x is differentiable, it is certainly continuous, so this goes to 0 as h goes to 0. And h2, which is y t naught plus h minus y t naught, that goes to 0 as h goes to 0. So this implies epsilon 1 goes to 0, epsilon 2 goes to 0 as h goes to 0, because as h goes to 0, h1 goes to 0, h2 goes to 0, and hence epsilon 1 goes to 0, epsilon 2 goes to 0. But there are some more things to take care of. What about limit h going to 0, h1 by h? That quantity also appears here, you can see. And here, here I will get h2 by h, okay? So what do they go? Again I write down the definition. It is limit h going to 0. What is h1? It is x t naught plus h minus x t naught divided by h. So this limit I know is x prime at t naught. So finally, similarly h2 by h, limit h going to 0, h2 by h, then is y prime at t naught. So finally what do I get if I look at the final difference quotient? So the first term goes to fx at x prime t naught, second term goes to fy at y prime t naught. The third terms, that is the term here, this goes to 0 because epsilon 1 goes to 0, and the remaining term h1 by h, that goes to x prime at t naught, that I have checked. Now I look at this term, this also goes to 0 because epsilon 2 goes to 0, and h2 by h, that goes to y prime at t naught. So as a whole, the whole limit turns out then to be equal to final result of the limit, that turns out to be fx at x t naught y t naught times x prime at t naught plus fy at x t naught y t naught times y prime at t naught. But this is precisely what has been claimed in the theorem, that the derivative of w is given by this sum of the products. So this proves chain rule for us. In the next lecture, we will go to the geometric interpretation of the derivatives, its relations with tangents and things like that.